Okay, we're going to continue on here, and I believe we finished 11, right? That's last time. I feel like it was a long day of lecturing. All right, so we're off to 12, I think. So I think we're getting near the end of the next couple exam, or what's going to be on the next exam. So chapter 12 here is we're going to talk about bonding and chemical bonding. We're going to talk about the two types of bonding. And really, as we will see in this chapter, the two types of bonding that we'll talk about, one's an ionic bond. And as we'll talk about, that's really between a metal and a nonmetal. And based on those sort of periodic trends that we talked about in the previous chapter, what we're going to really see with this is the metals have all those periodic trends where they want to basically give away their electrons. If you remember, the nonmetals pretty much have all those periodic trends of they wanted to basically hang on to their electrons and take other people's electrons. So when we get these two guys together, we actually get a transfer of electrons that occurs. And that creates an ionic bond that's going to create a positive guy and a negative guy, the electrostatic attraction that's going to hold that bond together. We will also talk about in this chapter covalent bonding. And covalent bonding is a little bit different. It's usually between two nonmetals. And also, really, because of those periodic trends we talked about in the previous chapter as well, those nonmetals both have the same sort of trends of they both want to keep their electrons. They also want other people's electrons. So what happens when we get two nonmetals together, as we'll talk about in this chapter, is essentially we'll get some sharing of electrons that will occur. And that's sort of the major difference between the two types of bonding, as we'll talk about in this chapter. One, pretty much there is no sharing of electrons. We have these kind of complete transfer of electrons from one place to the next. And the other one is that they will share electrons. So to help us sort of understand bonding and both types of bonding there, ionic bonding and covalent bonding, we sometimes will use Lewis dot symbols to help us do so. They are now usually kind of generically just called electron dot symbols, but some people still call them Lewis dot symbols. And basically, when we look at electrons within an atom, there's two different types of electrons. And again, if we just take lithium, for example, or 1s2, 2s1, thank you. We basically have outer electrons, which are our valence electrons. And in this case, lithium would have one valence electron. And then we also have core electrons, which are, again, closer to the nucleus. They're really not involved in bonding. So it is just those valence electrons that are involved in bonding. So when we draw Lewis dot symbols and later when we draw Lewis structures, we only show basically the valence electrons because those are the ones that are basically involved in bonding. A reminder that the number of valence electrons equals the group number. So again, you do not have to write out the electron configuration to figure out how many valence electrons somebody has. You got your periodic table and the group number there. My periodic table was big enough there. I'll make it bigger. It will equal the number of valence electrons. So everybody in group 1 has 1, 2, 3, 4, 5, 6, 7, 8. These again are our normal numbering or representative numbering of a periodic table. The one exception for that is group 8, and that is helium is the one exception, and that's because helium only has a total of 2 electrons, so it can't have 8 valence electrons, so it has 2 valence electrons because it only has a total of 2. But everybody else in group 8 will have 8 valence electrons. So our Lewis dot symbols are simply the symbol, and basically we use one dot to represent each of the valence electrons. There's really no certain rule, if you will. A lot of times people kind of put one dot per side and then go back and sort of pair it up if necessary. There really is no rule, like I said, but perhaps the only rule is it's really no more than 2 per side. So we don't put more than 2 dots per side. That's kind of the only real main rule there. And that means that if we look at it, we have 4 sides, 2 dots per side. That means we can max out here at 8 electrons. And as we will see in bonding, 8 electrons is an important number, is what's known as the octet rule. And that's pretty much what everybody wants to achieve. And just a preview, we'll talk about it more as we go on, but who has 8 electrons, valence electrons on the periodic table? Group number 8, which is the noble gases. And that is really the goal of all bonding is, as we might talk about when we're doing electron configuration with ions, the goal of all bonding is for everybody to achieve the same electron configuration as noble gases as they're really, really stable. And that is really sort of the goal of both types of bonding, ionic bonding and covalent bonding. The only exception to that, as we will talk about, but never hurts to talk about it early, which is, again, hydrogen. If you look on the periodic table, hydrogen only needs to get to what noble gas comes right after hydrogen? Yeah, helium. So hydrogen should never, ever, I'll say it 3 more times because it's worth it, ever, ever, ever have more than 2 electrons. Yeah, so if you're laying up a lot of electrons on hydrogen as we go through this chapter, you should also lay up a big X on it because it's probably wrong. Yeah, so should only have 2 electrons total. Everybody else, obviously, which is past helium, needs to get to group 8 to get those 8 valence electrons and be like those noble gases. So here's an example of some Lewis dot structures there, or symbols that I made one time when I was bored, so I should get a hobby. But you can see there, everybody in group 1, group 2, 3, 4, 5, 6, 7, 8. And once again, we do see our exception I was talking about there. Helium, because it only has 2, does have only 2 valence electrons. And that, again, as I just mentioned, why hydrogen only needs 2. It just needs to basically jump over there. Everybody else needs to jump into this column over here, basically with there. They have 8 happening. So as I mentioned before, we can use these to really talk about the 2 types of bonding. And again, ionic bonding is a metal and a nonmetal together. And that should be almost automatic for you. If you see a metal and a nonmetal coming together, that is definitely the type of bond it's making. It's going to make an ionic bond. You don't really have to really question it or anything like that. Covalent bonding, again, is going to be our 2 nonmetals coming together. And as we talked about earlier, and we'll talk about again as we go through this chapter, again, the major difference here is how those electrons end up. One case with our ionic bond, again, we're going to get that transfer of electrons. In the case of covalent bonding, we're going to get sharing of electrons. The general rule is if something with low ionization energy tend to form cations. So a reminder again, ionization energy is that energy required to remove an electron. So if you have a really low ionization energy, then it's going to be super easy for you to give up an electron, basically. And that happens when you go left and down on the periodic table, is those guys with low ionization energy. Ones with high electron affinity, again, electron affinity is the energy change that occurs when somebody gains an electron, and that increases up and to the right on the periodic table. And since they typically increase up and to the right, that means that they're pretty much prone to accepting electrons and gaining electrons and becoming negatively charged. So obviously to the left there, we're going to get some cations, and pretty much up into our sort of non-metal region, up right of the staircase, we're going to get our anions. So let's take a look at an example of what will happen here in a formation. So first off, I see lithium, which by the way, again, is a metal. I see fluoride, which is a non-metal. So once again, as I mentioned a second ago, automatically we should be thinking ionic bond basically in this situation because of that. And in this case, we could represent sort of what's happening here by sort of looking at our Lewis symbols. And lithium, which is group 1, will have 1 electron there, 1 valence electron. And fluorine, which is group number 7, will then have 7 valence electrons here. And if we look at the electron configuration for each of these, we got a little 1s2, 2s1 action. That right there being the 1 valence electron that we see in the picture. For fluorine, a little 1s2, 2, I'm going to say that right, 1s2, 2s2, 2p3 there. That's a really bad S, almost like a PS there. I should get rid of that there. Got that fixed, I think. All right. So in terms of fluorine, obviously these are the guys on the second energy level. There's 5 electrons there, and that's some bad math there. That should be 9, huh? So that should be. I feel like I missed a 5 there. There you go. That's better. So 2s2, 2p5. That's a little better. So that's our 7 electrons. I'll learn math eventually. I'll get a calculator. It'll be good. So this is what's going to happen. So basically, because we have our periodic trends of our metal there is going to want to give away its electron. Our nonmetal is going to definitely want to accept this electron. What we're going to have here is actually a transfer of that electron. So we're going to get that electron to actually transfer from the lithium to the fluorine in this case. The result of that is we're now going to get some things with charges. So our lithium will now become +1 charge as it has lost an electron. Our fluorine will then pick up that electron. Put it in red, maybe. Put it right there. And now, because it does pick up that electron, it will now also gain a negative charge in this case. So this is really why things do gain charges, because of those periodic trends. When they get near each other, what happens is going to happen, which is, again, that metal is going to be no problem giving up the electron. The non-metal is going to be looking to gain that electron. So here it is enough to pull the electron away, basically, from lithium. And now these guys do have charges. What happens to our electron configuration in this case? Our lithium loses that electron and now becomes 1s2 over here, as it has 1 less electron. Our fluorine gains the electron right there into that subshell. And now we have 1s2, 2s2, 2p6. And if we look at what has happened, lithium with a +1 charge now has 2 electrons. And again, on the periodic table, 2 electrons is helium, right? And if we look at the fluoride ion here, it now has 10 electrons, and on the periodic table, 10 is neon. So we have now just done what we want to do here in terms of bonding. Lithium has now achieved noble gas configuration in terms of electrons by losing an electron, and fluorine has gained noble gas configuration by accepting that electron from lithium, and now we have a really stable sort of bond that's going to happen. The other thing that you should notice when I draw these pictures for ionic bonding, which is charges, yeah, so you should indicate the charges here. And typically speaking, when you draw these for ionic bonding, usually people also incorporate some brackets around one, if not both of them. And the charges are necessary here because it does indicate that those electrons are not being shared. So again, what is holding this together is no sharing of electrons. It is solely the electrostatic attraction between those bonds there, the charges there, the positive and negative charge is holding that together. So once again, absolutely no sharing of electrons. So when you do draw these things in terms of ionic bonding, you do need to show the charges to indicate that. Any questions on that? Yeah. How do you apply this? So this is the purpose of this is how these ions come together when these elements come together and form an ionic bond. It is also the basis, for example, when we talk about nomenclature and writing formulas, why the formulas are the way they are, which is the simplest way possible to get no charge. So I think we talked a little bit about it earlier when we were talking about putting like a positive charge and negative charge together. We want it to equal 0 in terms of the overall charge. The real reason for that is this. That allows each of these guys to, in the simplest way, reach noble gas configuration, which is ultimately the most stable sort of situation that they want. Yeah. And it creates a really strong bond. So that's probably one of the strongest attractions you could have is sort of this electrostatic attraction, positive and negative attraction between it. Yeah. Yeah, so it is, and again, it is basically going to be necessary to get to an overall charge of 0. So that does require sometimes different amounts of each ones to come together properly. And we'll see an example of that in just a second. Other questions? Okay. So let's take a look at, that's what we just did. Good look at it. So again, as I mentioned before, that is what is referred to as an ionic bond. Once again, no sharing of electrons, simply that electrostatic attraction between the positively charged cation, which comes from the metal, and the negatively charged anion, which comes from the nonmetal. Now, if we take a look at another example here of calcium oxide, so calcium is group number 2, which means it has 2 valence electrons. And calcium is number 20 up there, so that's a 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. And those two right there are the 2 valence electrons that we see in the picture. You obviously could also shortcut this to argon, 4s2 if you like in that case. Now we have oxide, which is oxygen, and oxygen is group 6, which means it has 6 valence electrons, and it has 8 total electrons, so 1s2, 2s2, 2p4 in this case. So once again, we have a metal, and we have a nonmetal. So once again, that should be your signal. We are dealing with an ionic bond. And we always know in an ionic bond, pretty much this is always what's going to happen. We're going to send some electrons over to the nonmetal. So in this case here, we're going to get our electrons. The calcium is going to give away 1 electron there. Now in this particular case, because calcium's got 2 valence electrons, it actually does need to give away the second electron as well. So if you look on the periodic table where calcium is, if it only gives away 1 electron, it just backs up to potassium, which is not noble gas configuration. So it does want to give away both of those electrons. And it's able to do so, again, because the ionization energy is not terribly too bad to do so. It does get higher, as we talked about, when that second electron gets removed. But it's going to lay up right there. And at that point, what we will end up with is now calcium will gain that positive 2 charge as it has lost those electrons. And once again here, our oxygen is going to be the acceptor of those electrons. And because this oxygen accepted 2 electrons, it also will now end up with a charge, which is a -2 charge. Once again here, that is what is holding that together, that electrostatic attraction. And if we look at our electron configuration, we have now given up these 2 electrons here, which means it now has 18 electrons, or 1s2, 2s2, 2p6, 3s2, 3p6. And as we see on the left there, that is the same configuration as argon. The oxygen is going to put those 2 electrons right there in the p subshell because it's got room, right? Because the p subshell could hold up to 6, and it has only 4 at this pace. And that will give us 1s2, 2s2, 2p6, and that is now 10 electrons, which gives our oxygen, our oxide here, a noble gas configuration. Once again, we have met what we are looking for, which is we have hit noble gas configuration for both of these, creating a really stable bond. And again, that is really the goal, as I mentioned, of all bonding, is to reach that noble gas configuration for everybody in the simplest way possible. And that creates a really good, strong, stable bond that occurs between those things. Question on that there. Now, to answer your question of sort of what happens, let's say we actually put both of those things together, or a couple of those things. Let's say we took the calcium that we were just looking at, that has our 2 valence electrons, our argon, 4s2, which again, these are our 2 valence electrons. And let's say we put it together with fluorine from the first example there, which has our 7 valence electrons, 1s2, 2s2, 2p, they're 9, right? So 5. Let me get that right. I can't do the 5 today for some reason. 1s2, 2s2, 2p5. And in this particular case, we're going to see the same thing. This again is our metal, non-metal. So we're going to get a transfer of electrons from the calcium to the fluorine. So here we're going to send our electron over to the fluorine. At this point, can that fluorine take any more electrons? It cannot. It is actually full. Is calcium going to be happy just giving away one electron? It's not, for what I just said a second ago. That would only move it back to potassium, right, which is not a noble gas configuration. So in this case, calcium needs to give away a second electron to achieve that stable configuration of the noble gases. That fluorine cannot accept anymore. So to maybe answer your question you were asking a second ago, we would actually need not one fluorine in this case, but we would actually need a second fluorine in this case. And that second fluorine is going to give a place for that second electron from calcium to give away. And at that point, calcium has now given away, and obviously it has the same electron configuration as the other fluorine to start with. And that calcium has now given away two electrons, one to each of the fluorines, and now we'll end up with a +2 charge. Each of the individual fluorines here has gained only one electron, and what we will end up with is a fluorine here, for example, that has gained only one electron. I'll just like circle it here. And that also means because it only really gained one electron, it has a -1 charge, but we also have a second fluorine that did the same as well and has gained one electron there and now also has a -1 charge. And when we look, yeah, 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 it does. I think I'm going to answer your question in like 1 second, I think. So if not, let me know. But I think what you're asking is what we're going to talk about here in just a second. Okay. So in this case, when we look at all three of these guys, we end up with calcium that has lost two electrons, which are essentially these. And it now ends up with 18 electrons, which means this calcium has reached argon's configuration, which is really the goal here. Each of these fluorines has picked up one electron, which they can accept in this p subshell. And that's going to give each of these fluorines now 10 electrons, which means this fluorine here and this fluorine here has both reached neon's configuration. And that allows all three of them to be stable and create a stable bond. Once again, no sharing of electrons here, just the attraction between the positive and negative there that's holding that together. Now, if you remember when we talked about writing chemical formulas, these are basically the charges that each of these guys make. And remember that when we put these guys together, we want to make sure that we have no charge overall, right? So in this case, we have a +2 on this side. We have a -1 on this side. So we actually do need one more of these guys to give us another -1. And that balances out to give you the proper formula for calcium fluoride, which is that right there. So that is really why when we talk about putting together a metal and a non-metal, or a positively charged ion and a negatively charged ion, the overall charge does need to equal 0 in the simplest way. And the behind reason for that really is the bonding reason. By doing that in the simplest way to get it to equal 0, the positive guy and the negative guy together, you actually end up with a really stable bond between all those things in the correct bond. Yeah. Yeah. So they will not necessarily I put it this way, I guess they might not necessarily cancel each other out is the right word, but what they're really the goal of what they're really trying to do is in most cases end up with 8 valence electrons, everybody. And what that is we're going to put everybody to the noble gas configuration in terms of electron configuration. And the result of that, when a metal and nonmetal come together, is the metal typically will always lose enough electrons to kind of back its position up on the periodic table to the noble gas that comes before it. And the nonmetals will gain enough electrons to kind of push them forward. Now, and again, in some cases, you may need kind of more of each to correctly kind of balance that and get everybody to that. And that's really why when we talk about the formula for an ionic compound, like we have there, calcium fluoride, we want to get it to zero in the simplest way. And by getting to zero in the simplest way, when you balance it out, what that allows, like I said, is basically everybody to perfectly get to that kind of noble gas configuration in terms of their electrons. Because we clearly could get this to zero, right, by, for example, if we did like 2 calciums and 4 fluorines, right, that would get to zero as well. But we want to do it in the simplest way possible because we really don't in reality need that many of each of those elements to get everybody to balance out the valence electrons. We just need, in this case, like 1 and 2 to get us there. Yeah. It is actually, yeah. So it is a diatomic molecule, and that is the way it comes. And if we were to correctly sort of do it, you would have both of those, but I just was showing you individually here. Yeah. 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 Y- You mean when we put it together for the formula, like on the bottom? Exactly. So whenever you take anything that is a cation, which has a positive charge, and you take a anion, which is a negative charge, when you put those together properly to write the formula for an ionic compound, the overall charge has to equal zero. Now, even though it does equal zero here in the box, it's actually still made up of things that have charges. So it's still made up of these guys that actually do have charges, but they're sort of balanced and allows everybody to get to that noble gas configuration. Other questions? Okay. All right. So ionic bonding, again, is different than, say, covalent bonding. So we're going to talk about covalent bonding now. And covalent bonding is between two nonmetals. And once again, we do get a different sort of setup that occurs here. Because it is two nonmetals, what happens because of those periodic trends we talked about, if you look on the periodic table, all the nonmetals are pretty much piled together in the same location. And because they are piled together in the same location on the periodic table, they share similar periodic trends like ionization energy, electronegativity, electron affinity. They all have pretty much the same deal, which is they want to hang on to their electrons, and they also would like to kind of bring electrons towards themselves and try to gain some more electrons. So when you get two nonmetals together, the problem is neither one of them wants to give away their electrons because they're both looking to gain electrons. So what happens in that situation is the best that they could sort of agree upon is neither one of them is going to lay up their electrons to somebody else. So they're just going to agree upon sharing those electrons. So in this case, when we get two nonmetals together, we will have sharing of electrons because of that. Now, because we have sharing of electrons in this case, we will have actually different degrees of sharing, if you will. So we'll talk about it. That sharing can be equal sharing, or considered equal sharing, and it can be unequal sharing. So there is some aspect of sharing is going to happen in each case, but in certain cases they'll agree upon we'll just kind of share it kind of equally between us. And in some cases we will have them going, we'll share it, but I'm not going to share equally. I'm going to kind of pull them closer to me than you, but you can still hang on if you want. Like a tug of war sort of situation, guy pulling really strong on the rope, the other guy's kind of hanging on and being dragged around, but he's still hanging on. So they're still sharing, but some is a lot equally and some very much unequally. So Gilbert Lewis, which is why we call them Lewis structures usually, um, identified covalent bonding as really the sharing of electrons. So when we have something like hydrogen, which remember is a nonmetal, and it comes together with another hydrogen, for example, because obviously they're the same element and they're both nonmetals, what's going to happen in this case is they're going to decide we're just going to share these electrons rather than any electrons transferring. And what we end up getting is these two electrons that are now, in the case of hydrogen, being shared between them. And when we count in terms of electrons, those two electrons in the middle count for the hydrogen on the left, and the two electrons in the middle count for hydrogen on the right. That effectively means that the hydrogen on the left has two electrons, and the hydrogen on the right also has two electrons. Now, when we think about hydrogen and two electrons, that's good because, as we said earlier, hydrogen just needs to get to what element? Helium, which is number 2. So by hydrogen sharing electrons in this case, it's able to get 2 electrons for both of them. They both will now technically achieve that stable noble gas configuration and be happy in this situation. We could also represent that bonding without the dots and represent it with a line. And a line represents basically 2 dots or a single bond. So basically one line is a single bond. And again, that represented by basically 2 dots. As we'll talk about a little bit later on as well, 2 lines is a double bond. And that is basically 4 dots or 2 pairs of electrons. And there's also a triple bond. Which is basically 6 electrons or 3 pairs of electrons being shared in this case. So covalent bonding, again, is very different. We have actually sharing of electrons, and as I said before, equal or unequal sharing, but some aspect of sharing happens. So just like when you kind of see a metal and a non-metal together, you should know it's an ionic bond and you have transferring of electrons. When you see 2 non-metals together, you should know it's a covalent bond and you have some type of sharing basically happening of those electrons in this case. That is also why we do not end up with things that have charges. These are not ionic. They don't have charges. They don't make ions. And that's because we're not getting a transfer of electrons, for example, right? In this case. Yeah.
It's better with whether the dots are aligned.
It doesn't, to be truthfully honest with you. You can use either one. I personally and most people, I would say, would use lines to show the bond. But it is not incorrect at all to use the dots to represent it as well. So you can use both. But I'd say most people, when they're kind of doing it later, when we do Lewis structures, most people will use lines to represent the kind of bonds. But again, it's not incorrect at all to use dots. So in a covalent bond, what we actually have happening is there is an attraction between, for example, the electrons that are being shared and the nucleus of both atoms, right? So there's a nucleus of both atoms, which are positively charged. We have these negatively charged electrons in between the atoms. So they're going to feel an attraction to the nucleus on the left, also an attraction to the nucleus on the right. And that's sort of what locks them in place between them, is that kind of mutual attraction to both of the nucleuses and kind of keeps those electrons kind of bound between them. And once again, the sharing, no transferring in this case. So if we take a look at fluorine, for example, fluorine, which is F2, fluorine has, again, an electron configuration of 1s2, 2s2, 2p5. So once again, in this case, we would have one fluorine with 7 valence electrons, another fluorine with 7 valence electrons. And again here, definitely going to end up sharing these electrons here rather than transferring. And the result of that is we will actually end up with a bond here between the fluorine, where again, as we were just talking about a second ago, you can represent it with dots. You also, again, can represent it with the line that shows those electrons being shared, or the bond, if you will, and just use dots on the other ones if you want. Once again, in this case, by sharing electrons, our fluorine on the left there, if we count it up, 2, 4, 6, 8 electrons. Our fluorine on the right, again, sharing those electrons in the middle, 2, 4, 6, 8. So once again, in this case, each of the fluorines, through sharing of electrons, is able to achieve the magic number there of 8 and be like the noble gases and create, again, a very stable bond. Bless you. Any questions on that there? So when we look at this, there are some different types of electrons in these sort of structures. So first off, all these electrons here that are not involved in bonding, and we know they're not involved in bonding because there's no other element written on the other side of them or anything like that. These are what are referred to as non-bonding electrons, or if you're old like me, lone pairs. So if somebody says lone pairs or non-bonding electrons, they're talking about the same thing. They're talking about really the electrons not involved in a bond. Yeah, two electrons together. Yeah, so this circle here, those two would count as a lone pair, and all the two that are circled out. So in this case, there's also some other electrons, obviously, that we were talking about, which is the two electrons right here, right, that's being shared in this case. And that one also has a really creative sort of name because that is being shared to make a bond. Those are known as bonding electrons. Yeah. So bonding electrons are the ones, obviously, that make a bond. Non-bonding electrons or lone pairs are the ones that do not make bonds. Yeah. No, so bonding electrons are also basically pairs of electrons. Usually is how you count them. And again, remember that although we do have one line there in this particular case, it does represent two electrons in that case, right? Yeah. Other questions? So you should, when you draw these Lewis structures, and we're going to talk about officially later on how to draw Lewis structures correctly, but you should always show in your pictures both the bonding electrons and the non-bonding electrons. The non-bonding electrons or lone pairs should be shown as dots like that. They really, nobody does this too much anymore, but sometimes you'll even see people kind of do that for it. And if you take some organic, sometimes they do that. But don't do that in here. Show them as dots is typically the way that you should show them. All right, so a Lewis structure, again, is a representation, like I said, of covalent bonding, where, again, we use those dot symbols to show those bonding electrons. Again, either way is correct. A line are dots if you want to use for bonding electrons. And our non-bonding electrons are our lone pairs, which should always be shown as dots. And remember, though, that the only electrons that we are seeing in these pictures are the valence electrons. Each of these elements obviously have those core electrons still available to them, but they're not involved in bonding, so we don't show them. So, when we see something like lithium with just one valence electron, you remember, though, lithium does have 3 total electrons. It just happens, for example, just to show the one in those pictures. Another example of this sort of sharing to get everybody to the right one is water, for example. So once again, if we look at water, water is actually sharing some electrons. The oxygen is sharing electrons with some hydrogens. So this oxygen, by actually sharing electrons with both of the hydrogens, is able to achieve 8 valence electrons. Remember, it did start with 6. And that is our friend hydrogen, which, as we talked about a number of times, has 2 electrons, which it needs by sharing with the oxygen, and 2 electrons. So in the case of water, we're able to create these really stable bonds by sharing electrons between the oxygen and the hydrogen, once again allowing everybody involved in this bond or this molecule to achieve that stable configuration. And that's, again, pretty much the goal of bonding, is to get everybody involved to that stable situation. And that ultimately creates a lot of good things that happens. It creates a really stable bond, creates a really stable in terms of energy as well of those bonds. Everything's nice and stable and allows it to basically stay together. Otherwise, we create these bonds that aren't really stable, things are just going to fall apart, right? So the goal here is to minimize really energy of the bonds and get everybody into that nice, stable, noble gas configuration. Any questions on that? Yeah. Hydrogen is a non-mineral, yeah. It is. It is. I agree with everything you just said. Other questions? All right, so obviously we've been talking about it around it, but officially here, getting to those 8 valence electrons is what's known as the octet rule. And again, that's pretty much the goal. And everybody will basically continue to make bonds until they have 8 valence electrons around them. Obviously, our one exception there being hydrogen, as we talked about, it will stop at 2. So once again, for just a friendly reminder, if you are doing some type of Lewis structure down the road and you're drawing hydrogen that looks like this, although most people will just go full in and go everything to it, that is like way, way, way too much. You're going to get a big X. Yeah, so don't do that. So pretty much hydrogen should look like that. It also means that hydrogen should never, ever, when we talk about drawing Lewis structures for covalent bonding, hydrogen should never, ever be in the middle. And because if it's in the middle, it's going to definitely have more than one bond. Yeah. So hydrogen always has got to be on the outside, basically attached like that, one bond in. By the way, the hydrogen rule is sometimes referred to as the duet rule, meaning again that it only needs 2 electrons there to be happy. So we talked a little bit about it a second ago, but here officially, again, a single bond is where we share 1 pair of electrons. That is a grand total of 2 electrons. And again, it can be represented by 1 line or 2 dots, which represents a pair of electrons, as we saw in fluorine. Now, in certain cases, to get everybody to that octet rule and be really stable, that's all they need. Everybody just needs to lay up a single bond. But in other cases, to get people to get to the octet rule and be stable, sometimes a double bond is necessary to get there. And in this case, for example, a double bond is represented by 2 lines, like we see, for example, in CO2. We need a double bond actually on both sides here to allow our carbon to get to 8 electrons. So by making a double bond, the carbon between each of the oxygens, that will actually allow the carbon to get to the octet rule. It also allows the oxygen to still maintain the octet rule by sharing. So sometimes, as we'll see when you're drawing these pictures, single bonds is not sufficient enough to get everybody to that stable state. You do have to make a double bond. And again, that's 2 lines or 4 electrons total, 2 pairs of electrons. You could also have a triple bond. And in some cases, a triple bond is necessary to get everybody to the octet rule. So for example, nitrogen needs to actually triple bond with itself to get each nitrogen to get to 8 electrons. In the case of C2H2 over there, we also need to triple bond the carbon to allow everybody to get to 8 electrons. A triple bond, again, is basically 3 lines represented by 3 pairs of electrons or 6 total electrons. With that being said, as we'll talk about when we talk about drawing Lewis structures, you should not double bond and triple bond out of the box. So people always want to like just lay up some bonds all over the place. So it's really a good idea in most cases, as we'll talk about, starting with single bonds and then only kind of going to double bonds or triple bonds to fix something that doesn't have the octet rule. That usually leads you to the best structure that you can draw rather than just trying to like double bond or triple bond right out of the box with everything. So just keep that in mind as we get going into drawing some of these things. Before we do that, we're going to talk about a really important sort of periodic trend a little bit more than we did when we were talking about periodic trends, and that is electronegativity. And as we talked about, electronegativity is the ability of an atom to bring electrons towards itself. And remember that on the periodic table, right, electronegativity increases this way and decreases this way, with fluorine being the most electronegative element you could have. So fluorine is the most electronegative element you could have. By the way, that is because to the right of fluorine is the noble gases, and they're perfectly happy the way they are. They're not looking to do anything. And if you remember sort of what we were talking about on Monday, as you go up group 7, reactivity increases, right? So fluorine is the most reactive one that we have. So electronegativity enables us to figure out how electrons, for example, are going to pretty much be shared. So as I talked about before, when we're talking about covalent bonding, usually we use electronegativity to help us decide what type of covalent bonding we're having. Are we having a covalent bonding where the sharing is equal? Are we having the covalent bonding where the sharing of electrons is unequal? And electronegativity really helps us sort of determine that. So for example, if we think about our hydrogen example, because they are both hydrogen, they both basically in this case have the identical electronegativity values, right? So they both have the identical, I'm going to pull the electron so much one way or the other. So what happens in this case is, if my really bad lines here represents the electrons, we get kind of like an equal sharing of electrons between them. And they're going to end up sharing those electrons pretty equally. Kind of like if you're thinking about like a tug of war type situation, each person is pulling the rope equally. The little flag in the middle is just going to kind of stay there, right? But it's not going to go anywhere, fall or anything like that. It's suspended because there's an attraction to each side, and that's what holds them together. Again, same idea as how those electrons are held between them. This type of situation where we have equal sharing of electrons is what is referred to as a nonpolar covalent bond. Or for the most part, people leave the covalent part off and just say that is a nonpolar bond. So sometimes you'll hear people just say nonpolar bond. People may say nonpolar covalent bond. It is basically the same thing. It is really the equal sharing of electrons between two nonmetals. Yeah. Absolutely. So well, no, let me say this correctly. Any diatomic element, which I think is what you're asking, yeah, that's the same element would be. So remember, diatomic in general just means that it's two elements basically together, or two atoms together. But if they are two atoms that are the same, which are elements, they will absolutely be nonpolar because they will share it equally. Yeah. Other questions on that? So what happens though when we get something like HF? So if we take away one of the hydrogens and say we bond it now with our fluorine, in this case, there actually is a big difference in electronegativity. If you look at where hydrogen is versus fluorine, and fluorine being the most electronegative element there is, the electrons are not going to be shared equally in this case. The electrons should head towards which element? The hydrogen or the fluorine? Yeah, because it's the most electronegative. So he's going to be the one kind of the tug of war pulling a lot harder than the hydrogen, right? And that's going to end up causing, and again, if these lines represent the electrons be hanging out, a lot more of the electrons hanging out towards the fluorine side than the hydrogen side. And that also affects what we see because if the electrons are hanging out more towards the fluorine side than the hydrogen, would the fluorine side be more positive or more negative? Yeah, because the electrons are hanging out there. So what ends up happening as a result of this unequal sharing of electron is the fluorine creates a partially negative charge. That's a delta symbol, and it refers to a partially negative charge. The hydrogen, because the electrons are kind of heading away from it, will create a partially positive charge. And unlike what we had in our nonpolar bond, which is essentially a neutral bond, there is no charge because they're sharing those electrons equally. In a bond like this, because of the unequal sharing, we actually get a bond that has charges on either end of the bond. And we end up with a partially negative charge or a partially positive charge. We could also represent this with a arrow. And in this case, the arrow would actually point towards the more electronegative atom. And the back end of the arrow, which kind of makes like a plus sign right about there, it points to the positive side of that bond. And again, the arrow point of the arrow points to the negative side of the bond. This type of sharing of electrons is what is known as a polar covalent bond, or just a polar bond, most people will call it. And that is a result of unequal sharing of electrons. So they are both covalent bonded, they are both sharing electrons, But in one case with our nonpolar bond, because of the equal sharing of electrons, we basically get a neutral bond, no charge happening. In our polar bond, because of the unequal sharing of electrons, we end up with partially positive charges, partially negative charges, and we do end up with a bond that kind of has a positive side and a negative side to it. By the way, why is it only a partially positive charge and a partially negative charge? Why is it not a full positive charge and full negative charge? Yeah, the electrons in this case is still being shared. So there's still some aspect of sharing that's happening here. Unlike an ionic compound that we talked about, there's absolutely no sharing. So those electrons fully transfer from the metal to the nonmetal, and that creates a full positive charge for the metal and a full negative charge for the nonmetal in an ionic situation, because the difference in electronegativity and all those periodic trends are a lot bigger than we have when two nonmetals get together. So when two nonmetals get together, we'll either share equally or we'll get unequal sharing. But it's not so unequal sharing that those electrons actually jump from one to the next. The positive guy is still holding on. Yeah, so, and there's different degrees of holding on. Some are just barely holding on, like this case actually. This is like just barely holding on the hydrogen. And others are, holding on pretty tight, each of them, but still a little bit unequal. Any questions on that there? Yeah, either one. That's it's a delta. Yeah, it's a delta symbol, and it represents partially positive and partially negative.
Why separate then because like the oxide and then fluorine has H.
Yeah, exactly. So what it creates in terms of not just the electrons, but overall, there's like bond energy associated with it. There's like a lot of energy when things come together and make bonds. By doing this and getting everybody to kind of that noble gas configuration, it ultimately kind of lowers everything to a nicer sort of energy level as well. And that also creates a very nice stable bond that keeps it together. Yeah. Other question? Yeah. You could, you wouldn't really, in this case, in a sense, do the electron configuration because, again, we're not really getting a full transfer of electrons in this case. So we don't really have an ion that sort of changes. In a sense, because they're sharing, it does count for both of them. But it doesn't really sort of become charged in that case because it's still being shared. So we wouldn't really do sort of electron configuration more for covalent bonding, like we do for sort of ionic bonding. Other questions? All right, so as I mentioned before, again, the electrons in this case, because of that unequal sharing due to electronegativity, will create this sort of charged bond, which is known as a polar covalent bond, or again, just most people would just call it a polar bond. So usually if you hear the terms polar bond or non-polar bond, it's really implied in most cases that we're talking obviously about a covalent bond. So that's why a lot of times people will kind of leave that out. And that's because when we talk about an ionic bond, that's pretty much how it's referred to. It's referred to as an ionic bond, and that would refer to a metal and a non-metal together, no sharing of electrons. So here's sort of the same idea. By the way, that arrow, as I mentioned before, this is what is sometimes referred to as a dipole arrow. And dipole, as we'll later talk about as well, basically kind of means that something that has a dipole basically is something that is not sharing electrons equally. Yeah. What's that? Oh, over here? Yeah, no, it's just basically sort of representing the electron density in a really bad picture, but it's just trying to show that a lot more of the pink's electron density is hanging out over there by the fluorine versus the hydrogen over here. And again, that's what's going to create that partially positive over here and partially negative charge, over there. It's a little bit different. That actually has to do with more so the number of electrons that are present and how many bonds there are. And we'll get to that towards the end of this chapter. But in terms of the shape of the molecule, to answer it, and we'll explain why in a bit. But basically, the shape of this molecule is actually linear straight, basically. And the quick answer for why that is, and we'll talk more about it later, but it's basically you have only two things, right? And where they say the only way you can connect two things is a straight line, yeah? And that's the only way you can kind of connect two things in that case, yeah. Other questions? So really when we talk about electronegativity, what we're talking about again is usually helping us decide in a covalent bond, is it going to be a polar bond or a nonpolar bond? Are we going to expect kind of equal sharing or unequal sharing of electrons? You can also, as we'll talk about, use electronegativity for ionic bonds, but truthfully, you don't really need it because an ionic bond is always a metal and nonmetal. So as long as you know that's a metal and nonmetal, you don't even have to think about electronegativity. You know you're going to get an ionic bond that's going to happen. So when we talk about sort of our three types of bonding that we talked about, we have on sort of one end of the extreme, we do have our ionic bond. And our ionic bond, as we talked about, is always a metal and a nonmetal together. And we are always going to get a transfer of electrons in this case. That's going to create our cation, right, which is positively charged from our metal. It's going to create our anion that is negatively charged from our nonmetal. That's going to hold together through that electrostatic attraction. No sharing of electrons here. An example, obviously, is something like sodium chloride is an example of that, or any of the ones that we did at the beginning. On the other end of the extreme, we have sort of a nonpolar covalent bond. And that is between two nonmetals. That is sharing of electrons. That is actually equal sharing of electrons. And an example of that would be like our H2, our F2 as well. Any of those guys. Sure. And in the middle of those two, we have really our polar covalent bond. Also between two nonmetals. And that is going to be unequal sharing of electrons. That's going to create what we have right here, which is our example, a partially positive charge, partially negative charge. So again, at one end of the extreme with ionic, we get just a complete jump of electrons from one to the next, creating ions. And those ions with the positive and negative charge is what holds them together. On the other end, we have two nonmetals that are going to share those electrons equally, going to create a nonpolar bond where we have basically no charge associated with it. It's like a neutral bond, if you will. And in the middle, we have unequal sharing electrons, not so unequal that it jumps from one to the next like we have an ionic, but not equal sharing of electrons like we have in a nonpolar. We have some degree of unequal sharing between those electrons. That is what's going to create that polar bond where we end up with a partially positive side and a partially negative side to that bond, because again, we have that unequal sharing of electrons. Any questions on any of that there? Got it. So how do we know, are we going to really get sort of a nonpolar bond or a polar bond, or occasionally really even an ionic bond? We do want to look at electronegativity, and electronegativity really is the sort of overwhelming periodic trend that we look at to try to help us decide really between polar and nonpolar. And electronegativity obviously is related to the electron affinity and the ionization energy. And fluorine, which has a high electron affinity, which means it likes to gain electrons pretty much, and it has high ionization energy, which means it doesn't like to give away its electrons, would have a high electronegativity. Something like sodium, which is a metal, has low electron affinity. It's not looking to gain any electrons, and it has a very low ionization energy, which means if you just look at it wrong, its electrons are going to pop off. It doesn't take a lot of effort for it to lose its electrons, so it has low electronegativity. And I could draw out the electro there in that one. So a guy by the name of Pauling actually came up with calculations of electronegativity values for each of the elements. And you could use Pauling's scale to help you decide, are you going to expect to get equal sharing, unequal sharing of electrons? And basically, Pauling's scale goes from 0 to 4. 4 is the most electronegative. 0, not so much. Yeah. So you could calculate what is sometimes referred to as the change in electronegativity. So delta En, change in electronegativity. And basically what you would do is you would take Pauline's values for each of the elements that are involved in the bond, and you simply subtract them. So all you have to do is just take the two values and subtract them. You would subtract them in a way that gives you a positive number. So, whichever one's larger, just subtract the larger from the smaller. And if you subtract the values and you get a difference between 0 to 0.4, that is considered a nonpolar bond. And that means that you would expect those electrons to be shared equally in that case. If you do the difference in electronegativity and you're above 0.4, so you're basically above 0.4, which is usually 0.5, to below 2, so basically 0.5 to below 2, you will have some type of polar bond. If you're above 2, typically, you will have some type of ionic bond, basically. So basically 0 to 0.4, nonpolar, equal sharing of electrons. Basically 0.5 to less than 2, polar bond, unequal sharing electrons. And above 2 will be an ionic bond. The ionic bond is not perfect above 2. There is differences where it's less than 2, but it's still an ionic bond. So again, what I mean by that is I wouldn't even worry about electronegativity for ionic bond. All you need to worry about is what we talked about. Metal, non-metal is what you should think about. But again, it's just a rough cutoff for ionic around 2. But you really don't need the values to determine that. You just need to determine metal, non-metal is going to be ionic. Now, if you happen to have, for example, a difference in electronegativity of 0, like perfect 0 there, that is like perfect equal sharing of electrons, basically. That is sometimes also referred to in books and stuff as a pure covalent bond. That is still a nonpolar bond, but people will sometimes call it a pure covalent bond because the difference in electronegativity is 0, and that's like the best you could do, right? So it's the best you could do in terms of equal sharing of electrons between those two. So sometimes people will classify that difference of 0 as being a pure covalent bond. It's still a nonpolar bond, but sometimes people will just refer to it that way as well. Any question? Yeah. Yeah. It will hit somewhere in that range. You won't be off. It won't go more than won't go more than 1 decimal place usually. So you'll be in good stuff. If, unless you have a really detailed scale. Most scales are kind of like wholish numbers or to the 1 decimal place. So usually that's as far out as you have to worry about.
Sorry, what?
Just the 2 elements involved in the bond. So this is what is sometimes used for what is referred to as bond polarity. So in a bond, it's basically just two atoms, basically. And you're just taking the 2 atoms or the 2 elements that are involved in that bond, and you're going to subtract them. So let's take a look at a scale. So here, this will hopefully help you here. So this is, again, Pauline's sort of scale. As you can see on the left-hand side of the periodic table, the values are small, like 0.9, 0.8. As we roll this way, we start to get larger numbers all the way up to fluorine, which is a value of 4, right? So if we were to look at, for example, our ones that we were talking about, we take our sodium chloride example, we take our F2 example, and we take our HF example that we did, right? So how we would do this, for example, is we would take our sodium and look up the value of sodium. And the value of sodium there is 0.9. So that is 0.9 for that guy. Chlorine, which is over here, is a value of 3. So to calculate the change in electronegativity, we basically just take 3 minus 0.9. That is a 2.1 difference, I believe. And 2.1 is above 2, and that would tell us it is a ionic bond. This is an example of a case where you don't really need the numbers because I know sodium is a metal and chlorine is a nonmetal, so I know it's ionic. You really don't need the electronegativity values to do that. So I would roll with that rule of metal, nonmetal, ionic without even worrying about it. You should be right pretty much every single time. Now, if we go to our fluorine and fluorine, fluorine on the table there is 4. So that's 4. That is 4. So when I do the difference in electronegativity, that is 4 minus 4. Well, that is 0, right? So that falls between that 0 and 0.4. That is a nonpolar bond, right? Equal sharing of electrons. That would also be considered a pure covalent bond, right? Because it is a perfect equal sharing of electrons. If we come over to our hydrogen, hydrogen is 2.1. Fluorine is 4. So difference in electronegativity going to be 4 minus 2.1, 1.9, yeah? 1.9 is just below 2, right? So that is going to be our polar bond, right? That also means, is hydrogen holding on tight or just barely holding on in this case? Yeah, he's just barely holding on, right? Because he's almost at 2-ish level of we're going to transfer electrons. This is one where we can again draw our arrow pointing to the more electronegative atom. And again, that arrow is what is referred to as a bond dipole arrow. So I'll draw it down here. So that arrow is, again, what is referred to as a bond dipole arrow. And it represents within that bond that the fluorine is more electronegative than the hydrogen, and the fluorine is more positive, more negative than the hydrogen, which is more positive. Question on that. Clearly the values would be given to you. Yeah, so these values would be given to you. You don't have to memorize them or anything like that. You do need to know, though, the general trend in electronegativity, increasing to the right, decreasing, down to the left, but you don't have to memorize actual numbers. So let's take a look at, not that. That is the only one I got, huh? All right, so why don't you try some here? Let's get rid of all the scribble I just did there. Why don't you decide, is it going to be a ionic bond, a polar bond, or a nonpolar bond? If we do the bond between carbon and oxygen, the bond between carbon and hydrogen, the bond between, we'll do carbon and sulfur. We'll do nitrogen and phosphorus. And why don't we do like potassium and fluorine? All right, so for each of those, use the electronegativity values to decide, is it going to be polar, nonpolar, or ionic? 2.5, and oxygen there is 3.5. So if I do my difference in electronegativity, I'm basically going to take 3.5 minus 2.5. That is a difference of 1. And that falls between obviously 0.5 and 2. So that's going to be a polar bond. And that would mean the arrow, if I was to draw it, should point to which element? Arrow should point to the more electronegative element, which would be the oxygen in this case, yeah? That would mean the oxygen is more negative in this bond versus the carbon that is more positive in this bond. Question on that one there. Yeah. You would use this as a good question. You would actually use this individually for each bond. So in CO2, there's a carbon-oxygen bond and another carbon-oxygen bond. You would use this difference in electronegativity only for one bond at a time. Yeah. And that will allow you to compare all the bonds, or all the bonds polar, all the bonds nonpolar. You absolutely can have, as we will see, a combination of that. You could have some bonds in a molecule that are polar, and you could have some that are nonpolar as well. So you would do it for each individual bond. Yeah. Other questions? And in the case of CO2, both of the carbon-oxygen bonds on each side would actually technically be polar. Yeah. All right, so if we look at carbon, which is 2.5, and hydrogen there is 2.1, my difference in electronegativity is going to be 2.5 minus 2.1. That is 0.4. 0.4 is actually nonpolar, right? It is the 0 to 0.4. The reason it goes to 0.4 is actually for that bond right there. That is carbon and hydrogen. That's what a lot of organic molecules are, which are nonpolar, and it's actually a nonpolar bond. Even though it's considered a nonpolar bond, are the electrons actually being shared perfectly equal in this case? They are not, right? They are slightly being pulled closer to the carbon, right? But not enough to be considered a polar bond. So they're still considered equal sharing of electrons in that case. We would not draw an arrow on this because it is equal sharing of electrons, yeah? We go for carbon and sulfur. Once again, carbon 2.5, sulfur there 2.5. That is a difference in electronegativity of 0, right? That means the carbon-sulfur bond is actually nonpolar. So this is an example that you actually can have two different elements that are nonpolar, and it's because of the position on the periodic table. If you look at carbon and you look at sulfur, they're what are referred to as having a diagonal relationship. Carbon is further up, but sulfur is further to the right. They actually are diagonal of each other and cancel out their differences. And there's a few places where that occurs. You could also see it with nitrogen and chlorine, diagonal to each other. They're not right underneath each other diagonal, kind of diagonal and over one. And that will sort of cancel out the relationship. Just to finish these last two here for today, we got nitrogen that I just scribbled on there, which is 3. And we got phosphorus, which is 2.1. Difference in electronegativity in this case would be, I'll just do it there, 0.9. 0.9 is above a 0.4, and that would make this a polar bond, where we should have actually the electrons heading towards the nitrogen in this case, and we would draw the arrow going in that direction. This, we don't really even need the electronegativity because I know it's a metal, non-metal. That is going to be ionic, yeah? Any questions on that there? All right, couple things